got some glasses, and you don't need the glasses the whole time. If you want to, it'll give you a really trippy experience, but I just have a demo in a couple of minutes that I wanted to show you with them. So you can set them aside for right now, and then we'll use them in a few minutes. So I wanted to start off with this picture of the night sky. And this is a picture taken from a dark location. And if you go out away from city lights, you can see about 2,000 to 3,000 stars with your naked eye on any given night. Now, of course, that depends on what night you're looking and where you are, but it's roughly around 2,000 to 3,000, how good your eyesight is, something like that. And for most of human history, we haven't had what's called light pollution. We haven't had street lights out at night, or car lights, or parking lot lights, or anything that we need to see in the dark, right? People used campfires, candles, but they didn't put off a whole lot of light, so you could still see the stars. So for most of human history, we've actually been able to see the sky like this, and we don't see it that much these days. So I wanted to show you a picture of what the night sky actually looks like. And for thousands of years, people have been looking up at the sky, they see these stars, and they make up stories about what is up in the sky. So here's Orion, up in the sky, a famous winter constellation. And it's a picture, right? It's a picture of what we used to imagine the sky was. It was a bunch of stories. And today we still tell stories, but we use more sophisticated means to see what the stars are telling us about. Now, for a long time, the stars, they made sense. They didn't really change much. You would see them come and go throughout the seasons. They rise and set throughout the night. But they keep their same patterns. So whenever you look at Orion looks like this. There's not really a lot of change to Orion whenever you see it. But there were a couple of things in the sky that were different over time, and they confused people for a long time. And these are things that you might have actually seen the last couple of nights out in the sky. This picture was actually taken just a couple of days ago in India, but it's the same night sky that we see, and it's a little faint here in this picture, but just after sunset, when the sky is starting to get dark, has anybody looked out into the west in the last couple nights? See the moon, and there were two other really kind of bright spots over by the moon. And those two things are planets. So it's Venus is the brighter one, and Jupiter is just a little bit above it in the sky right now. And these planets actually really confused people for a long time about what they were, because they actually wandered in the sky. The word planet actually means wanderer in Greek. So they didn't know what these things were. And it took a long time. It was about actually 400 years ago when the puzzle pieces started to fall into place. And it was this guy right here, Galileo Galilei. And he took a telescope for the first time and pointed it up at the sky. And when he did that, he saw things that nobody ever expected before. So this was right in the middle of a debate that was going on what the universe was like. And up until this point, people thought that the Earth was at the center of the universe. Because if you think about it, it kind of makes sense. If you watch the sun throughout the day, it looks like it kind of goes around the Earth. And if you watch the moon, it looks like it goes around the Earth. It rises and it sets. And the stars at nighttime, they rise and they set. It looks like everything's sort of going around the Earth. So from our perspective, it seemed like the Earth was at the center of the universe. Well, turns out we're not at the center of the universe. And one of the big discoveries that Galileo did when he took his telescope and he pointed at the skies, he looked at a planet, trying to figure out what a planet is. And he looked at Jupiter specifically. And this is, on the right-hand side here, are some of his own drawings of what he saw when he looked at Jupiter. And you'll see the kind of notes on the left of that are dates. And then the big circle is Jupiter, and then he saw some little dots next to Jupiter. He called them stars. He didn't know what else they were. He said, there's these stars next to Jupiter. And he went out a couple nights later and looked at it, and he said, oh, there's stars again, but they're not in the same relationship they are to Jupiter. And he went out several nights in a row, and what he realized is that these are actually moons going around Jupiter, and that something was going around Jupiter. So if the Earth was at the center of the universe and everything went around the Earth, well, here's something going around Jupiter. And it was a huge revelation to people that something could go around something other than the Earth. And this discovery, along with a lot of other things that Galileo did, I don't have time to go into tonight, convinced people that, hey, maybe the Earth isn't at the center of the universe, and maybe the Earth is going around the sun. And maybe these planets are going around the sun. And it turned out, when you look at the motions of the planets in the sky, it matches that they are going around the sun. And the Earth is going around the sun. So the Earth is a planet. The Earth is just like those other things that were wandering across in the sky. And so this brings the question of, well, if these things are wandering around in the sky, is there anything out there that's like Earth, right? So we now know that our solar system has the sun at the center, and the Earth is one of 8 planets that's going around it. There's a lot of other small things that are going around the sun. This picture has the planets and the sun to scale, but it doesn't actually have their distances away from each other to scale. We can't put those two things on the same slide, or we would be looking at pretty much nothing. So we have the sun here. Just to give you a sense of perspective, though, the Earth could fit about 110 times across the sun. So the sun's really, really big. Jupiter is the biggest planet in our solar system, and you can fit about 10 Earths all the way across Jupiter. So there are other planets out there. None of them are really like Earth, unfortunately, although some of them are like Earth in some ways and not in others. Here's a picture of the orbits now to scale, except again, we're kind of looking at it at a side angle, because if we zoomed out and looked at it kind of face on, again, it would be, everything's really spread out, is the idea. But I wanted to show you that on the inside are the rocky planets. The inside is where the Earth is. And you can see that that Mercury, Venus, Earth, and Mars are all very close to the sun on this scale. And then the bigger planets, Jupiter, Saturn, Uranus, and Neptune, are much further out. And I have Pluto on there too, which you may know is not a planet anymore. It is what we call a dwarf planet or a minor planet. So it's still out there. It's still something that's actually really cool. And then, this is a side note, but if you guys don't know, we have our first spacecraft headed towards Pluto right now. It's been traveling there for almost 9 years, and it's going to reach Pluto in about 3 weeks. So, yeah. In a couple of weeks, we'll get some really awesome pictures of Pluto. We have really actually no idea right now what even Pluto looks like, except a fuzzy blob. So, yes. Anyway, so Pluto's on there for scale 2 to kind of show you where Pluto is. But this is the stuff that's close by, actually. And we're still looking for, is there something else like Earth out there? So there are a couple of candidates. The one that's kind of closest in size and to the Earth, and the actually closest planet that ever gets to the Earth, is Venus. And Venus, though, this is a picture of Venus, and for a long time we didn't actually know what Venus was like, because Venus is really hard to observe. This picture was actually taken with ultraviolet light. It's not taken with visible light. And you can see that there's kind of there's some hazy clouds there. Really, if you look at Venus in visible light, it's this big white sphere. It's completely covered in clouds. And those clouds are reflecting all of the light, so we can't actually see what Venus's surface looks like. We couldn't see it for a really long time until we actually sent spacecraft missions to Venus that both landed on the surface and orbited Venus and used radar to see what the surface shape was like on Venus. But Venus it's about the same size as Earth, but that's kind of where the similarities stop. The surface temperature on Venus is over 800 degrees Fahrenheit. And those clouds that you're seeing are not made out of water, but sulfuric acid. There's more sulfuric acid in those clouds than there is in a car battery. So while Venus is sort of similar to Earth, it's many ways much, much different. Our next candidate would be Mars. This is a picture of Mars. And Mars is actually quite Earth-like. It's smaller than Earth. It's farther away from the sun. It has a thinner atmosphere, and it ends up being a lot colder on average than the Earth. Although it can get fairly warm in places and fairly cold in other places. It has seasonal polar caps, and at one point in time, it probably had a lot of liquid water on its surface, just like Earth does today. Although that water is no longer liquid, and a lot of it is no longer even on the planet. A lot of it has probably escaped to space. There's one other cool candidate in the solar system that I want to talk about, and this isn't actually a planet, but a moon of a planet in the solar system that's also kind of similar to Earth and one of my favorite places in the solar system. And this is Saturn's moon Titan. So Saturn has a moon Titan, and Titan's actually bigger than the planet Mercury, and it has its own atmosphere. It has a very thick atmosphere, actually, a thicker atmosphere than Mars, a thicker atmosphere than Earth even, but not quite as thick as Venus. It's about 1.5 times, the atmosphere is about 1.5 times as thick as Venus's atmosphere. And on the right-hand side over there, you can see is sort of what Titan looks like in the visible. It's very blurry and hazy. And over here, we can see a little bit more detail when we look at different kinds of light. And Titan, those dark spotches that you see on Titan, it's actually a liquid on the surface. Titan has oceans, or, well, seas, maybe not quite as big as oceans, lakes, rivers flowing on the surface of Titan. Now, it turns out that's not water, but methane and ethane. It's so cold on Titan, it's so far away from the sun that methane and ethane are liquid, and it rains liquid, and it rains liquid methane and ethane and pools and flowing rivers and things like that. So it's the only other place in the solar system where we have a liquid on the surface, and in that way, it's very similar to Earth, but also very, very different. So if we can't find a place like Earth in our own solar system, we could ask the question, is there another Earth elsewhere outside of our solar system? So we started with that picture of those stars in the sky. Here's another picture of the stars in the sky. And each one of those stars is like our sun. Our sun is a star. And each one of these could possibly have planets going around it. Now, a long time ago, well, not even that long ago, like 20 years ago, we thought that planets would actually be quite rare going around other stars. We thought our solar system was probably fairly unique in that we had all of these planets orbiting around the star. Thought we were kind of lucky because if you have so many different objects going around a star, it's likely that they get thrown out gravitationally with one object or the other object. And so 20 years ago, we thought it's actually probably really rare that there are planets going around. But about 20 years ago, we found the first planet going around another star. So a star far away, we detected a planet going around the star. And the way we did it is, this was supposed to be like animated and moving around, so you'll just have to imagine. If you have a star, which are the big circles over here on the left, okay, and then a planet, which are the smaller circles, the planet goes around the star, but the way gravity works is that gravity is pulling the planet close to the star, pulling the planet so it moves in an orbit around the star, but the planet actually pulls on the star a little bit too. And depending on the relative size of the two planets, the relative masses of the two planets and the relative masses of the planet and the star and how far away they are, they pull on each other in different amounts. So much so that, for example, in this case where we have a fairly small star and a fairly big planet, they actually are orbiting around a point that's in between the two. And so you see this center star actually wobbling in the sky. And when you see that wobbling, you can determine that something's pulling on it. The starlight's much brighter than the planet. And so you can see the star wobbling, and you can figure out if there's something there. Now, you're not always looking at things in this perspective, and actually even looking at these things in this perspective kind of face on like this, it's really hard to actually see a star wobbling like that. They're really far away. Even though they're really big, they're not really wobbling very much. So what we actually do is look at them kind of edge on, like that picture up there in the top. And this is where I want to do the little demo. Okay, so everybody can get their glasses out. So when you look at light, you can actually see a lot more. When you put your glasses on right now, what are you guys seeing? Rainbows, right? Yeah, lots of rainbows. And when you look at light coming from a star or from something else out in space, you can actually determine a lot of different things by looking at the light and breaking it up into a rainbow. There's a couple of people in the back. Okay, so I'm going to turn on this light over here up in the front, and I've kind of tried to place it so that most of you guys should be able to see it. And if you look carefully at this light, first of all, without your glasses, it looks orange, right? When you put your glasses on, you can see, and you look at that light, you should be able to see a lot more colors other than just orange. Yeah? This light right here, I can even like hold it up, if that helps. Yeah? Okay. All right. So you should see a bunch of lines. Yeah? Those lines, those different colored lines, they happen to tell us a couple of different things. One, they're telling us that this tube right here is a neon tube. So what's happening is there's a gas inside of this tube, and we electrify the gas so that it produces light. And that light that's being given off is coming from the neon atoms inside of the gas. All right, I'm gonna turn it off now. It's kind of loud. All right. Okay, so the specific lines that we have, anywhere we look out in the universe, we're going to see those exact same lines of neon. Okay, so neon in this tube is the same as neon out in a star or out in a cloud of gas out in space. So we can tell if an object is made with neon if we see that same pattern of lines. And those lines are always the same for neon, and they're different for different elements. So something made out of helium is going to have a different set of lines. All right. So when we look at a star has lines. The starlight has lines in it too. And instead of being bright lines like we just saw here, they actually have dark lines. So you see this rainbow picture up here. You see the dark lines taken out. Those dark lines are telling us what the star is made out of, but we know very specifically where those lines are supposed to be. And sometimes they aren't in the spots where they're supposed to be. So the top one you can see, that's the one where they're supposed to be. The bottom one, you can see all the lines have been shifted a little bit to the right, towards the red end of the colors. And the ones on the bottom, all those lines have been shifted just a little bit towards the left, towards the blue end of the rainbow. And so we call this red shifted or blue shifted, and that happens when something is moving, that's giving off light, that's moving towards us or away from us. And so when we look at a sun and a planet in a system like that up there on the top right, we can actually see if the star is wobbling because we can see those little lines shifting back and forth. All right, so every once in a while, you get a nice alignment just like this over here where you're looking at it edge on, and you can see the star wobbling, coming back and forth with you. But there's another cool thing that happens, is that planet can pass directly in between you and the star. And when that happens, the light from the star dips a little bit. And this actually happens in our own solar system sometimes. This is a picture of Venus going across the sun. So this is a projected image of the sun. This was actually taken at Pierce College in 2012, and Venus went right in front of the sun, and you can see that little dark spot on the disk of the sun. That's Venus going in front. And so we can see the same thing happening with other planets going around other stars. We can see this little tiny dip in the light from the stars because the planet is passing between us and the stars. So there's two different ways we can detect the planets then. One, we're looking at that little shift in the lines to see if the star is wobbling, and two, we can see if there's this little dip in the starlight. And it turns out that you have to have kind of a big planet to get a really big wobble, one that's easy to detect, but you can have a fairly small planet that's going in front of a star that makes just a tiny little dip, but we can actually detect it really well. So these two ways are actually one of several other, there's several other ways too where you can detect planets going around other stars, but these two are kind of the main ways. All right, so we built a telescope called the Kepler Space Telescope, and the Kepler Space Telescope is in orbit around the Earth. So it doesn't travel around space, it just stays in Earth, but it gets above our atmosphere so we can get a really clear view of stars. And it looks at a particular area of the sky, and it simultaneously measures the light from over 100,000 stars to look for those little tiny dips of planets going in front of them. And I should say it did. It died a few years ago. It doesn't work quite the same way as it did. But this is a picture of the telescope. You can see the size of it relative to the two people right there, and that's the area of the sky that it's looking at, or it was looking at. And here is kind of a graph of what it sees. So you can see the one right there. That's its average brightness. of this star. But every once in a while, that star, the brightness of the star just dips just a little bit as a planet passes in front. And you can see that dip is really, really small. On the side here, this is like a percentage, right? So you can see it's only like 0.02 or 0.03% of the starlight that is being blocked by the planet as it goes by. But the equipment is sensitive enough to detect that, which is really awesome. So we can detect little tiny planets going in front of these stars. So this is one of my favorite images here, because this is showing you the number of planets that have been detected versus time. And about 20 years ago, 1995, this is like one planet being detected in the late 80s and early 90s, but they were very speculative. It actually came like later. They had to get more confirmation. So like they were first kind of talked about here. The one where people really had very, very solid evidence was in 1995, so 20 years ago. And you can see that it took a long time for us to discover a lot of planets, right? So in the early 2000s, we knew of a couple dozen planets out there. And in 2005, which was 10 years ago, we knew of maybe a couple hundred planets total. And then now in 2015, we know of thousands of planets if you add up all of those planets that have been discovered over the years. We know of thousands of planets going around other stars. This is the planets, some of the planet candidates that just the Kepler Space Telescope has found. And this is actually out of date. You can't even fit all of the Kepler candidates on a poster anymore. Because there's like something like 4,500 around there. This is only 2,700 as of January 2 years ago. So you can see how rapidly things have gone up. And the picture, what you're seeing is the big circles are the stars, and then the dark circles within them are the sizes of the planets relative to the star. And you can see there's a huge variety in both size of star and size of planet. Up in the upper right, you can see Jupiter relative to the sun, to give you a little perspective. And based on how close these planets are to their star and how big they are, basically how much of the starlight they're blocking, we can estimate, sizes of the stars. Some of them we can even estimate densities. Is it a rocky planet or a gas planet? And we can estimate temperatures, too, of these planets, just based on some of the physical properties we can get. And these are kind of the most Earth-like planets out there, the most habitable ones. The ones that are the most Earth-like are in the upper left, and then they kind of go down to the lower right here. But it's a handful that are out there. So the title of my talk, though, tonight was, is anybody out there, right? Or are we alone, right? Is there life on any of these planets, right? If we're looking for something like Earth, is there life on any of these places? And the answer is, we don't know, right? So what do you want to do? I know what I want to do. I want to go out there. I want to go travel. But unfortunately, these planets are really, really, really far away. They are several light years to hundreds of light years away from us. And a light year basically is the time is the distance that light takes to travel in a year, which is really far. To give you an example, the sun is 93 million miles away. It takes light 8 minutes to travel from us to the sun. So how far could light travel in a year? a lot farther. It's like 10 trillion kilometers. So, but there are ways out there where we can actually look at these planets a little bit deeper and see if we can detect life on those planets even from really far away. And what's really cool is we started out, looking at stars with just our eyes. And then we got the telescope with Galileo. And then we have more advanced telescopes like the Kepler telescope that can detect these planets. But now we even have telescopes now that can look at the light coming from those stars when the planet is passing through. And as that light passes through if those planets have atmospheres, the light will pass through those planets' atmospheres. And just like how we saw the lines of neon right here, there will be lines in the light that hits our eyes that tells us what kind of elements are in the planet's atmosphere. So up here on the top, you can see kind of an idea of how this works. You have a star, and then you have a planet, and then you have a spectrograph, which is kind of like your glasses that you have, and you can see lines, all right? And those lines can tell you what's in it. And so if you were looking at those lines, you'd say, oh, that has sodium in it, or whatever. So this has been done for a couple of planets that are out there. None of the Earth-like planets yet, but some of the big Jupiter-like planets. This has worked. So we have, you can see here's a couple of big planets. We have some of the things that might be in them, in their atmospheres. They actually have detected water vapor on some of the atmospheres of these big planets too, which is pretty cool because that's one of the things we need to know for life. But if we think about it, if we were looking at the Earth's atmosphere, there's lots of things in the Earth's atmosphere that we could tell if we were looking at it from far away that there's life on this planet. For example, the oxygen, the O2 in our atmosphere, and even the O3, the ozone that's up higher in the atmosphere, or in higher concentrations up in the atmosphere, it's produced because life is on this planet. We would not actually have oxygen in the atmosphere. It was actually created by the first life on the planet. It was a waste product. Okay, we would not have O2. We wouldn't have other things in the atmosphere either in the proportions that we do, except for that there's life here on this planet. So when we go and we look out at stars and we see planets going around these stars, and now we're able to tell what's in their atmospheres, we're getting really close. We have the technology now to do it. We're getting really close to actually finding life somewhere else. And so it's my opinion, and not just my opinion, but other people are out there too, that in the next 5 to 10 years, we have the technology that we will actually detect life somewhere out there. We've got the numbers, and we've got the technology that if it's out there, we'll find it. So I know that we got to start the movie, so I just wanted to encourage you guys to, if you haven't ever been to the Science Dome, it's at Pierce College in Lakewood, and we talk all about science. We do mostly astronomy, but we do other science stuff too, and we do have public shows several times a week. So, all right, thank you.